It is difficult to fully grasp just how vast the distance between stars truly is, because even with the technology we have today, a journey to the nearest star system would take an almost unimaginable amount of time. Using conventional propulsion, a spacecraft would need somewhere between 1,000 and 81,000 years to reach Alpha Centauri. And along the way, any crew would be exposed to the many unknown hazards of the interstellar medium, a region we have barely begun to understand. Yet even within this seemingly impossible scenario, there may be a quiet and unconventional solution beginning to take shape, one that does not rely on large spacecraft at all, but instead on something far smaller and far lighter. One such idea is known as the swarming Proxima Centauri concept, a proposal that has attracted attention from NASA through its innovative Advanced Concepts program. Rather than sending a single large mission, this approach imagines thousands of tiny probes moving together, guided not by traditional engines, but by light itself. It invites a simple question that sits at the heart of interstellar travel. How do we cross such immense distances when speed, energy, and scale all work against us? The challenge becomes clearer when we consider the numbers more closely. Proxima Centauri lies about 4.25 light-years away, which corresponds to roughly 25 trillion miles, a distance so large that it stretches far beyond any journey humanity has attempted. For perspective, the most distant human-made object, Voyager 1 has traveled about 15 billion miles over more than 46 years, reaching speeds of only a few dozen miles per hour. At this pace, interstellar travel remains not just slow, but effectively impractical within any human timescale. And even if we could accept the time, the energy required for such a journey presents another barrier. Moving a large spacecraft across interstellar distances would demand resources far beyond what is currently feasible. This is why researchers have begun to consider an entirely different approach, reducing the spacecraft to something almost weightless, measured not in tons, but in grams. Here, the idea becomes both elegant and unusual. Instead of carrying fuel, these tiny probes would be pushed forward by photons, particles of light, reflecting off a thin laser-driven sail. Each photon carries only a minute amount of momentum, so to generate meaningful acceleration, an immense number of them must be directed at the sail. However, even with powerful lasers, the force produced would remain gentle, which means the probes themselves must be incredibly light. The proposal suggests using a laser system with a power output measured in the hundreds of gigawatts, focusing its energy onto these miniature sails and gradually accelerating them to a significant fraction of the speed of light. It is a quiet shift in perspective, moving away from heavy machines and toward delicate, almost invisible explorers, drifting through the darkness, carried not by engines, but by beams of light. If such a system could be realized, a powerful laser array would gradually accelerate thousands of these tiny probes, each equipped with a delicate light sail, pushing them to speeds reaching somewhere between 10 and 20% of the speed of light. At that velocity, a journey that once seemed to require tens of thousands of years could be reduced to a single human lifetime. Some projections suggest that development could begin around the middle of this century, with the first probes potentially arriving at Proxima Centauri as early as the year 2075. What makes this idea especially intriguing is not just the speed, but the structure of the mission itself. Rather than relying on a single spacecraft, researchers envision a coordinated swarm, possibly numbering in the thousands, each unit contributing a small piece to a much larger picture. Early studies have already explored how such a fleet could navigate the immense emptiness of interstellar space while still maintaining a fragile but continuous link with Earth. And yet, even communication introduces its own quiet limitation, because any signal sent across such distances would take about 8 years to travel there and back. making real-time control impossible. This delay changes the nature of the mission entirely. These probes would need to think for themselves, in a limited but meaningful way, deciding how to adjust their paths and which data is most valuable to send home. In a sense, they would become our distant representatives, operating alone in an environment where guidance from Earth arrives far too late to be useful. There is also the question of cost, which, while significant, may not be as prohibitive as one might expect. The most expensive part of the system would likely be the laser infrastructure itself, while the probes, being extremely small, could be produced relatively inexpensively. Some estimates place the total cost at around $100 billion, a vast sum, yet modest when compared to the scale of what such a mission could achieve. After all, the potential return is not just scientific data, but a deeper understanding of worlds beyond our own. And among those worlds, one stands out more than most. Within the Alpha Centauri system lies a small, dim star known as Proxima Centauri, and orbiting it is a planet called Proxima Centauri b. It is, in many ways, the nearest Earth-like planet we know. Its mass appears comparable to our own world, and it lies within what we call the habitable zone, a region where conditions might allow liquid water to exist. This alone makes it a compelling target. If water is present, and if an atmosphere exists, then the basic ingredients for life, at least as we understand it, could be there as well. But this is where certainty begins to fade. Proxima Centauri b might host life, or it might be nothing more than a barren, airless rock. At present, we simply do not know. Part of the difficulty lies in how we observe distant planets. Most exoplanets are discovered through what is known as the transit method, where a planet passes in front of its star and causes a small repeating dip in brightness. This method not only reveals the presence of a planet, but can also provide clues about its atmosphere. However, Proxima Centauri b does not pass directly between its star and our line of sight, which means this technique does not work in this case. Instead, astronomers detected it through a subtler effect. By carefully studying the light from its star, they noticed a slight wobble, caused by the gravitational pull of the planet itself. This method allowed scientists to estimate its mass and orbit. But beyond that, much remains uncertain. We cannot yet detect clear signs of biology, and we cannot directly observe its surface or atmosphere. This is why the idea of sending even the smallest probes becomes so meaningful. A swarm of lightweight explorers, traveling silently across the vast darkness, could one day provide answers that our telescopes cannot. And in recent years, the search has only intensified. Observations made around the years 2022 and 2023 have expanded our catalog of exoplanets beyond 5,000 confirmed worlds, revealing a remarkable diversity of planetary systems. Some are massive gas giants like Jupiter, others are icy worlds similar to Neptune, and many are rocky planets not unlike Earth. And yet, this is likely just the beginning. There may be more than 1 trillion such worlds scattered across our galaxy alone, which leads to a quieter, more fundamental question. Among all these distant planets, how many might truly be capable of supporting life? A few candidates have already begun to emerge, each offering a different possibility, a different kind of world. And among them, one in particular has recently drawn attention. A planet known as Wolf 1069b, a name that feels almost mechanical, though behind it may lie something far more familiar. A more recent study, involving around 50 astronomers and supported by NASA, has pointed toward another nearby world that quietly stands out. The planet, known as Wolf 1069b, orbits a small red dwarf star roughly 31 light-years from Earth. Based on current observations, it appears to be a rocky planet, similar in size to our own, and at least in theory, it may lie within the range where conditions could allow liquid water to exist. To find it, scientists relied on a technique known as radial velocity, a method that does not look for the planet directly, but instead watches how the star itself subtly moves. As a planet orbits, its gravity causes the star to shift ever so slightly, moving toward us and then away again. By measuring these gentle motions in starlight, astronomers can infer the presence of an unseen companion, estimate its mass, and begin to understand its orbit. It is a careful and indirect way of seeing, almost like noticing the motion of a hand by watching the shadow it casts. From these measurements, Wolf 1069b appears to have a mass a little greater than Earth, perhaps around 1 1/3 times as heavy. More importantly, it orbits within its star's habitable zone, a region where temperatures might allow water to remain in liquid form. If the planet possesses an atmosphere similar to Earth's, estimates suggest surface temperatures could rise to around 55 degrees Fahrenheit, warm enough for water to exist, at least on part of the surface. But, as is often the case, the details complicate the picture. The planet is likely tidally locked, meaning one side always faces its star, receiving constant light and warmth, while the opposite side remains in permanent darkness. This creates a world divided between extremes, where any potential habitability may exist only in a narrow region between light and shadow. For now, the data is not enough to say more, and it may take another decade of observations before clearer answers begin to emerge. And Wolf 1069b is not alone. Another intriguing discovery comes in the form of TOI 700e, a planet located about 100 light-years away. It is roughly similar in size to Earth and is thought to orbit within a region where liquid water could be possible. Unlike the previous example, this planet was detected using the transit method, where astronomers observe a slight dimming of a star as a planet passes in front of it. This technique relies on patience and precision. When a planet crosses the face of its star, it blocks a small fraction of the light, creating a repeating pattern that can be measured. By tracking these changes over time, scientists can determine the planet's size, its orbital period, and its distance from the star. In the case of TOI 700e, the planet completes an orbit in about 28 days, suggesting it lies relatively close to its host star. The discovery was made possible by the TESS mission, which has surveyed a large portion of the sky and identified dozens of confirmed planets, along with thousands of additional candidates awaiting verification. This steady accumulation of data is gradually reshaping our understanding of how common planetary systems may be. Yet even here, uncertainty remains. TOI 700e may also be tidally locked, much like Wolf 1069b, which could again limit the regions where stable conditions exist. It raises a familiar question, not simply whether a planet lies in the habitable zone, but whether it can truly sustain an environment where life might take hold. Moving even closer, astronomers have identified 2 additional planets, GJ 1002b and GJ 1002c, orbiting a nearby red dwarf star less than 16 light-years away. In cosmic terms, this distance is remarkably small, placing these worlds among our nearest planetary neighbors. For comparison, Proxima Centauri, b, the closest known Earth mass planet, lies just over 4 light-years from us. These discoveries, taken together, suggest something subtle but profound. Earth-like planets may not be rare exceptions, but rather a common outcome of how stars and planets form. And yet, even with this growing list, the deeper question remains unchanged. Among all these distant worlds, how many are truly alive, and how many are simply silent, waiting to be understood? These 2 nearby worlds, GJ1002b and GJ1002c, orbit a small red dwarf star with only about 1/8 the mass of our Sun. A star that burns faintly and quietly compared to what we are used to. Yet because both planets circle so closely, they still receive enough energy to fall within a potentially habitable range. One completes an orbit in roughly 10 days, while the other takes just over 21 days, meaning that on these worlds, the passage of time would feel very different, with years unfolding far more quickly than on Earth. Their discovery was not simple. It required careful coordination between international research teams and highly sensitive instruments such as Espresso and Carmenes, capable of detecting incredibly small shifts in starlight. The precision achieved is difficult to imagine. Measurements so refined that they begin to hint at the fine details of distant planetary systems. What matters most, however, is not just their proximity, but their nature. Both planets appear to be similar in size to Earth and lie within the habitable zone of their star, making them strong candidates for future studies of planetary atmospheres. Findings like these are gradually shifting our perspective. Instead of asking whether Earth-like planets exist, we are beginning to ask how common they might be. Each new system adds to a growing sense that such worlds may be scattered throughout our cosmic neighborhood, quietly orbiting their stars, waiting to be understood. Another example comes from a more distant system, where the planet LP8909c orbits a red dwarf star about 98 light-years away. This world is somewhat larger than Earth, perhaps around 40% greater in size, and it shares its system with a companion planet that is even larger still. That companion, however, is likely far too hot to support anything resembling life, with estimated temperatures reaching around 253 degrees Fahrenheit. A reminder that proximity to a star can quickly turn a world inhospitable. LP890-9c, on the other hand, sits within the habitable zone, placing it in a region where conditions might allow for liquid water. Yet even here, uncertainty remains. The true nature of its environment depends heavily on its atmosphere. If it has experienced a runaway greenhouse effect, similar to what we see on Venus, then it may be far hotter than its position alone would suggest, potentially making it unsuitable for life despite its promising location. To answer these questions, astronomers are turning to more advanced tools. The James Webb Space Telescope, launched in December 2021, is designed to study the atmospheres of distant planets in unprecedented detail. By analyzing the way starlight passes through or reflects off a planet's atmosphere, its instruments can detect the presence of gases, measure temperature ranges, and begin to assess whether a world might be habitable. Already, some planets have been ranked among the most promising candidates for habitability within a few dozen light-years of Earth. Yet even as this list grows, it brings with it a quiet reflection. While we search for other worlds that might resemble our own, it also reminds us of the unique conditions that make Earth what it is. The pace of discovery continues to accelerate. With each passing year, new planets are identified, new systems are mapped, and our understanding expands. There may be thousands, even millions more worlds waiting to be found, and scattered among them. Planets like those we have just considered remain distant and silent, orbiting their stars, unchanged by our curiosity. The search itself has become one of the defining efforts of modern astronomy, alongside the James Webb Space Telescope. Missions like TESS and Kepler, Space Telescope continue to scan the sky, collecting data, refining methods, and revealing patterns that were once invisible. But before we look further ahead, it is worth pausing to ask a simple question. Why do we search for Earth-like planets at all? Part of the answer lies in our growing ability to observe the universe with increasing precision. Advances in telescope technology have allowed us to measure starlight with extraordinary accuracy, revealing subtle motions that were once hidden. As planets orbit their stars, They exert a gravitational pull, causing the star to move ever so slightly, for a long time. This motion was impossible to detect, masked by the natural distortion of starlight as it passes through Earth's atmosphere. Stars appear to twinkle. But this twinkling is not a property of the stars themselves. It is an effect introduced by the air above us. The development of adaptive optics changed this. By making tiny adjustments to telescope mirrors in real time, scientists can correct for atmospheric distortion, stabilizing the light and allowing these minute stellar movements to be observed. With the twinkle removed, the subtle wobble caused by orbiting planets becomes visible, and with it, a new way of discovering worlds beyond our own. It is a quiet transformation, one that does not rely on dramatic breakthroughs, but on patience, precision, and the gradual refinement of how we observe the universe. And as our tools continue to improve, so too does our ability to ask deeper questions. Not just about where these planets are, but about what they might be like, and whether, somewhere among them, conditions have aligned in just the right way for life to begin. As starlight travels through Earth's atmosphere, it becomes distorted, creating the familiar twinkling we see when we look up at the night sky. For centuries, this effect masked something far more subtle, a gentle motion hidden within the light itself. But once that distortion is corrected using advanced techniques, something remarkable begins to emerge. The star no longer appears to shimmer randomly. Instead, it reveals a faint and steady shift, a small wobble caused by the gravitational pull of orbiting planets. This method, known as astrometry, allows astronomers to detect planets not by seeing them directly, but by observing how they influence their host star. The larger the wobble, the more massive or numerous the planets may be. Over time, by carefully tracking these patterns, scientists have been able to infer the presence of entire planetary systems, even when the planets themselves remain invisible. This realization marked a quiet turning point. Our solar system, once thought to be unique, was no longer an exception. Instead, it became one example among many. As more data accumulated, it became increasingly difficult to avoid a simple and profound question. If planets are so common, then is Earth truly special? Or are there other worlds like it scattered across the galaxy? The search for Earth-like planets has since become one of the most significant scientific efforts of our time. The scale of investment alone reflects this. Observatories and missions, such as the James Webb Space Telescope, the Kepler Space Telescope, and TESS represent years of planning, engineering, and global collaboration. Their combined cost reaches into the tens of billions of dollars, and that figure accounts only for the instruments themselves. Behind them stands an entire network of scientists, engineers, analysts, and researchers working across universities, space agencies, and institutions around the world. It raises an interesting thought. Why dedicate so many resources to finding another Earth? Part of the answer lies not in the expectation of immediate travel, but in the shift in understanding that such a discovery would bring. Even if reaching these distant worlds remains far beyond our current capabilities, simply knowing that they exist would change how we see our place in the universe. If we were to confirm that planets similar to Earth exist elsewhere, with liquid water, stable climates, and perhaps even atmospheres rich in oxygen, then space would no longer feel empty in the same way. It would become a landscape filled with possibilities. And in that realization, there is something quietly humbling. It may even deepen our appreciation for the fragile conditions that sustain life here at home. To carry out this search, astronomers rely on different methods, each offering a unique perspective. The Kepler Space Telescope and TESS primarily use the transit method, observing how a star's brightness changes when a planet passes in front of it. This moment, known as a transit, causes a small but measurable dip in the star's light. By studying these dips, scientists can determine several important properties of the planet. They can estimate its size based on how much light is blocked, and they can measure its orbital period by observing how often the dimming occurs. However, there is an inherent ambiguity. A large planet passing farther away from the star can produce a similar signal to a smaller planet orbiting much closer. This is where careful observation over time becomes essential. By combining multiple measurements and methods, astronomers can begin to resolve these uncertainties and build a more complete picture of distant worlds. It is a slow and methodical process, one that unfolds over years rather than moments. And perhaps that is what makes it so compelling. We are not simply discovering planets, we are learning how to see them, piece by piece, through the faintest signals carried across the vast distances of space. To truly understand what we are seeing, it is not enough to observe a single dimming of starlight. The orbit of the planet must also be measured, carefully and patiently, over time. This is why missions like TESS take a different approach. Instead of capturing isolated images, they record long, continuous observations of the sky, quietly watching hundreds of thousands of stars at once, looking for the faint and repeating signals of planets passing in front of them. Interestingly, TESS does not rely on a traditional telescope in the way we might imagine. Instead, it uses 4 highly sensitive cameras, each designed to monitor large sections of the sky over extended periods. These instruments effectively create long-duration recordings of starlight, allowing scientists to track even the smallest variations. The reason for observing so many stars at once is simple, though it reveals something deeper about the nature of planetary systems. For a transit to be visible, the alignment must be almost perfect. The planet has to pass directly between its star and our line of sight. Even a slight deviation means the event goes completely unnoticed. This makes transits relatively rare from our perspective. For example, the planet Venus crosses the face of our Sun only once every couple of centuries when viewed from Earth. And yet, despite this rarity, TESS continues to detect many such events simply by observing such a vast number of stars at once. From this, a quiet conclusion begins to emerge. If we are only able to see a small fraction of planets due to alignment, yet still detect so many, then there must be far more planets than we can directly observe, perhaps even hundreds or thousands of times more. It leads to a realization that feels both simple and profound. Planets are not rare. They are everywhere. Into this expanding search enters one of the most advanced instruments ever built, the James Webb Space Telescope. With its large segmented mirror, spanning over 21 feet across, it represents a new step forward in our ability to study distant worlds. It is not just a telescope, but a carefully engineered system designed to observe the universe in wavelengths of light that were previously difficult to explore. And yet, alongside the excitement, there is also a sense of quiet caution. History has shown that even the most ambitious missions can face unexpected challenges. When the Hubble Space Telescope was first launched, a flaw in its mirror caused its early images to appear blurred, requiring a complex repair mission several years later. That solution was possible because Hubble orbits relatively close to Earth, within reach of astronauts. The situation is very different for the James Webb Space Telescope. It operates far beyond the Moon, in a region of space where no human mission can currently reach. If something were to go wrong, there would be no direct way to repair it. Any adjustments would need to be carried out remotely, relying entirely on instruments and data sent back across millions of miles. Even its deployment required careful precision. Its mirror, made up of multiple segments, had to unfold and align perfectly to function as a single surface. This process alone takes months as each segment is adjusted with extreme care. Once operational, the telescope begins its work not by searching blindly, but by focusing on known targets. A significant portion of its early observations is dedicated to studying exoplanets that have already been identified, allowing it to build on years of previous discoveries. Unlike traditional telescopes that observe visible light, James Webb is designed to detect infrared radiation. This allows it to see heat signatures and subtle atmospheric details that would otherwise remain hidden. When it observes distant planets, they do not appear as clear images, but rather as faint points of light. Yet within that light lies a wealth of information, waiting to be carefully interpreted. And so, step by step, observation by observation, we move closer to understanding these distant worlds, not by seeing them as we see Earth, but by learning to read the quiet signals they send across the vastness of space. When the James Webb Space Telescope observes distant planets, it does not capture detailed images in the way we might imagine. At best, these worlds appear as faint points of light, sometimes slightly blurred if an atmosphere is present, and yet, within that faint light lies something far more valuable than a picture. It carries information. As starlight passes through a planet's atmosphere, certain wavelengths are absorbed by the gases within it. This creates a kind of spectral fingerprint, a pattern that can be analyzed to reveal what that atmosphere is made of. If gases such as methane, oxygen, or carbon dioxide are present, the telescope may be able to detect them. These are not direct signs of life, but they are clues, subtle indicators that help us understand the conditions on these distant worlds. From this spectral data, scientists can begin to build a quiet profile of an exoplanet. They can estimate temperature ranges, identify atmospheric composition, and assess whether conditions might allow liquid water to exist. In some cases, they may even begin to evaluate the possibility, however uncertain, that life could emerge or persist there. It is a careful process, one that does not provide definitive answers, but instead narrows the range of possibilities. But the work of the James Webb Space Telescope extends far beyond individual planets. It is also designed to study how stars and planetary systems form within vast clouds of gas and dust in the Milky Way. Understanding how these systems come into existence is essential, because it helps us place our own solar system into a broader context. Looking even further, the telescope can detect light from some of the most distant galaxies ever observed. These are galaxies whose visible light is obscured by dust or stretched beyond the visible spectrum due to the expansion of the universe. In infrared, however, they become visible again. These ancient structures formed not long after the Big Bang, and by studying them, we begin to trace the early history of the cosmos itself. In doing so, the telescope may also help us better understand the forces shaping the universe on the largest scales, including the mysterious influence of dark energy, which appears to drive the expansion of space at an ever-increasing rate. Each observation adds a small piece to a much larger puzzle. And yet, even as we look outward across billions of years and unimaginable distances, there is a quiet tendency to return to something closer, a nearby star system, one that has captured our attention more than most. Proxima Centauri is the closest star to our solar system, a small and faint red dwarf, significantly smaller than our Sun and far less luminous. It lies just over 4 light-years away, which means the light we see from it today began its journey several years ago. By comparison, sunlight reaches Earth in only a few minutes. If we were to attempt the journey using current technology, it would take tens of thousands of years, far longer than the span of recorded human history. And yet, despite that distance, our interest is not focused on the star itself, but on the planet that orbits it. Proxima Centauri b is slightly larger and somewhat more massive than Earth, orbiting its star at a distance of just a few million miles. While this may seem extremely close, The lower energy output of its host star means the planet still resides within the habitable zone. In other words, it occupies a region where temperatures could allow water to exist in liquid form. This balance is delicate. Too close, and a planet becomes overheated. Too far, and it freezes. Proxima Centauri b appears to lie somewhere in between, where conditions might be stable enough for water, and perhaps for life as well. But as always, the reality is more complex than the initial impression. And while the location of the planet offers a promising starting point, it is only one piece of a much larger and more uncertain picture. At first glance, Proxima Centauri b seems to sit in a position that should allow life to exist. Its distance from its star places it within a region where liquid water could, in theory, remain stable. But as observations have become more detailed, a more complicated and less reassuring picture has begun to emerge. Its host star, Proxima Centauri, is not calm or steady in the way our Sun appears to be. Instead, it is highly active, prone to sudden and powerful flares. In one observed event, the star briefly increased its brightness by a factor of 1,000 for a matter of seconds, releasing an intense burst of radiation. Even smaller flares, occurring more frequently, contribute to a persistent and harsh environment. For a planet orbiting so close, the consequences are significant. Proxima Centauri b is exposed to levels of radiation far beyond what Earth experiences, including an estimated hundreds of times more X-rays. Under such conditions, the long-term stability of an atmosphere becomes uncertain. Any gases surrounding the planet could be gradually stripped away, and surface water, if it ever existed, might be lost over time. There is also the matter of its rotation. The planet is likely tidally locked, meaning one side constantly faces the star, while the other remains in perpetual darkness. The day side would be subjected to continuous radiation, while the night side would exist in a much colder, shadowed environment. This creates an extreme contrast across the planet, raising questions about whether any region could maintain stable, life-supporting conditions. And yet, even within this harsh scenario, there remains a narrow space for possibility. Some have suggested that if an atmosphere were thick enough, it might redistribute heat between the two sides, softening the extremes. Others have speculated, more cautiously, about the potential for life to exist beneath the surface, shielded from radiation. These ideas remain uncertain, but they illustrate how even the most hostile environments can still invite careful consideration. At one point, interest in this system intensified following the detection of an unusual signal. Observed over a period of about 30 days by radio telescopes on Earth, it appeared as a strong and coherent burst, unlike typical natural emissions. For a brief time, the possibility was raised that it could have an artificial origin, perhaps even linked to activity within the Proxima Centauri system. However, as further analysis was conducted, the most likely explanation shifted towards something far more familiar: interference from human technology. The signal has not been observed again in the same form, and without repeated evidence, it remains an unresolved anomaly rather than a confirmed discovery. Still, moments like this reveal how thin the boundary can be between observation and interpretation. A single signal can open the door to profound questions, even if it ultimately leads back to more ordinary explanations. Looking ahead, much of what we hope to learn about this system may come from continued observations using instruments like the James Webb Space Telescope. Positioned far from Earth, in a region where gravitational forces, balance, and interference is minimal, it operates in an environment free from atmospheric distortion, clouds, and light pollution. With its large mirror and sensitivity to infrared light, it is capable of detecting extremely faint signals from distant objects, including potential atmospheric signatures and thermal emissions. In some cases, It may even be possible to distinguish between natural and artificial sources of light, though such detections would require careful verification. Beyond individual planets, the telescope also allows us to look deeper into the universe than ever before, observing light that has traveled for billions of years. In doing so, it effectively gives us a view into the past, revealing how the earliest stars and galaxies formed, and how the universe evolved into its current state. And yet, even as we extend our vision across cosmic history, the question returns to something closer. Worlds like Proxima Centauri b remain just beyond our reach, close enough to study, yet distant enough to remain uncertain. They exist in a space between what we can measure and what we can truly understand. If there is life there, it has adapted to conditions very different from our own. And if there is not, then the reasons why may be just as important as the discovery itself. If we were ever able to detect something as subtle as artificial light on a distant world, it would represent a profound shift in our understanding, perhaps the first quiet indication that intelligent life exists beyond our solar system. And yet, even such a discovery would need to be approached with caution. Observations can be misinterpreted, signals can have natural explanations, and data can be incomplete. In science, certainty is never claimed lightly. In the end, there is only one way to move beyond interpretation and into direct understanding. We would need to go there. But even for the closest star system, Proxima Centauri, the challenge remains immense. With current technology, a journey would still take tens of thousands of years. For perspective, Voyager 1 has spent more than 4 decades traveling outward, and has only just begun to leave the boundary of our solar system. In comparison, the distance to another star is vastly greater. This is why new approaches are being considered. One idea involves sending extremely small probes, each no heavier than a fine needle, launched in large numbers. A carrier spacecraft would release perhaps 1,000 of these tiny explorers into space, where they would unfold thin, reflective sails designed to capture the momentum of light. By directing a powerful laser beam toward these sails, the probes could be gradually accelerated to a fraction of the speed of light, perhaps reaching around 20% of that ultimate limit. Even at such extraordinary speeds, the journey would still take more than 20 years, followed by several additional years before any data could be transmitted back to Earth. It is not a fast process, but compared to conventional travel, it represents a dramatic step forward. Still, Proxima Centauri is only one of many possible destinations. The search for life extends far beyond a single system, and one of the central roles of the James Webb Space Telescope is to expand that search across many nearby stars. Its instruments are sensitive enough to detect planets with temperatures similar to Earth, and to study dozens of nearby systems in detail, including not only planets, but potentially their moons as well. As observations continue, the number of known worlds is expected to grow rapidly. Each new detection adds another piece to a much larger map, one that is still incomplete, but steadily becoming clearer. At the same time, the telescope also turns its attention closer to home. Within our own solar system, there are places that may harbor the conditions necessary for life, hidden beneath surfaces that appear cold and lifeless. Europa, for example, is covered in ice. Yet beneath that frozen crust, there may be a vast ocean, warmed by internal forces generated through its interaction with Jupiter. A similar possibility exists on Enceladus, where geysers of water vapor erupt from beneath the surface, hinting at a dynamic and possibly habitable environment below. Using its infrared instruments, the James Webb Space Telescope can study these worlds in greater detail, searching for subtle chemical signatures that might indicate biological activity. These are not direct signs of life, but rather traces, small clues that point toward processes we are still trying to understand. Looking further ahead, even more ambitious observatories are already being planned. One concept, known as LUVOIR, envisions a telescope with a mirror far larger than anything currently in operation, capable of observing distant planets with even greater clarity. Such a mission could expand our reach even further, allowing us to examine the atmospheres of Earth-sized planets in ways that are currently beyond our capabilities. And so, the search continues, not as a single effort, but as a progression of ideas, technologies, and observations. Each building on the last, we are still at the beginning of this journey, learning how to see, how to measure, and how to interpret what we find. Somewhere out there, answers may already exist, but for now, they remain just beyond our reach, waiting quietly in the light of distant stars. Future observatories may travel even farther from Earth, reaching distances of around 1 million miles before beginning their quiet work of observation. From such a position, far beyond the interference of our atmosphere, they would look outward with extraordinary clarity. It is tempting to imagine what might come next. Perhaps, by the time these instruments have completed their surveys, our understanding of physics will have advanced enough to allow faster ways of crossing the space between stars. And if a truly habitable world is confirmed, the idea of sending not just machines, but people, may no longer feel entirely out of reach. For now, though, these possibilities remain distant, and so we continue to do what we have always done. We look up. For most of human history, we have searched the night sky, wondering whether life exists somewhere beyond our world. But there is another perspective that is easy to overlook. If we are looking outward, then it is just as possible that someone, somewhere, could be looking back. Recent studies suggest that there are thousands of star systems within our galaxy positioned in such a way that they could detect Earth using the same methods we use to find distant planets. In fact, more than 1,700 nearby systems may have had the opportunity to observe our planet as it passes in front of the Sun. This event is known as a transit. From our perspective, it is one of the most effective ways to detect exoplanets. But from elsewhere in the galaxy, the same method could reveal us. If an observer were located at just the right angle, they would see a small, subtle dip in the brightness of our Sun as Earth moves across its surface. It would not appear as a clear image, but as a slight and measurable change in light. From this, they could estimate the size of our planet, its orbit, and perhaps even begin to infer the presence of an atmosphere. We can observe similar events from here. The planet Mercury occasionally passes across the face of the Sun, appearing as a small dark point over several hours. This happens only a handful of times each century. Venus does the same, though far less frequently, with transits separated by more than a century in some cases. These events remind us how precise the alignment must be. For most observers, in most locations, such transits would never be visible at all. And yet, despite this limitation, we know that many stars are positioned just right to see Earth in this way. Among those, scientists have identified a smaller group of planets that may be especially interesting. Around a few dozen worlds. Conditions could be similar to those on Earth. These planets appear to be roughly comparable in size and orbit within the habitable zones of their stars. Regions where temperatures may allow liquid water to exist. If life has developed on any of those distant worlds, it is possible that for thousands of years, their inhabitants could have been aware of Earth as a potentially habitable planet. They might have seen the faint signal of our transit, just as we search for theirs. It leads to a quiet and humbling thought. The search for life is not only about finding others, it is also about understanding that we, too, may be part of someone else's search. And in that shared perspective, the universe begins to feel just a little less empty. For a planet to remain potentially habitable, it must exist within a delicate balance, not so close to its star that water evaporates into nothing, and not so distant that it freezes into solid ice. In that narrow region, where temperatures allow liquid water to persist, the basic conditions for life may begin to take shape. And because water is so fundamental to life as we understand it, these regions have become the focus of our search. What is quietly remarkable is that some of these distant worlds may have already seen us. Over the past 5,000 years, while human civilizations were rising and shaping the early structures of culture and knowledge, certain planets positioned at just the right angle could have observed Earth as it passed in front of our Sun. From their perspective, our planet would appear as a faint and repeating signal, a small dip in starlight that hints at the presence of a world orbiting within a habitable zone. One such example lies near the star Ross 128, where an exoplanet roughly twice the size of Earth orbits within a favorable region. For a period of around 2,000 years, this planet would have had a clear view of Earth's transit, but due to the gradual motion of stars through the galaxy, that alignment has now shifted. For nearly 900 years, Earth has no longer been visible from that location in this way. Another opportunity exists near Teegarden Star, about 12.5 light-years away. There, the geometry is slowly changing, and within a few decades, Earth will begin to pass into view once again. From that point onward, any observers in that system would have the chance to detect our planet using the same methods we rely on. Then, there is the Trappist 1 system, home to a collection of at least 7 planets, several of which lie within the habitable zone. However, the alignment there is not yet favorable. It may take many centuries before Earth becomes visible from that direction. Time, on a galactic scale, moves slowly. Still, observation is only one form of connection. There is also communication, though even that is shaped by distance and limitation. Since the late 19th century, Earth has been emitting radio signals into space, spreading outward at the speed of light. These signals form a growing sphere around our planet, carrying fragments of our presence into the surrounding stars. If there are civilizations within a few dozen light-years, it is possible that our earliest transmissions have already reached them. But communication is not immediate. Any reply would take just as long to return, meaning that even a simple exchange could span decades. There is also a deeper uncertainty. Radio communication assumes that another civilization uses similar technologies, or even recognizes the signals as meaningful. It is entirely possible that life elsewhere may follow different paths, using methods of communication we do not yet understand, or none at all. And yet, we continue to reach outward. In the year 1974, a deliberate attempt was made to send a message into interstellar space, known as the Arecibo message. It encoded a simple but symbolic summary of humanity. Within it were representations of numbers, elements, the structure of DNA, a human figure, and a diagram of our solar system, with Earth slightly highlighted. It was not expected to receive a reply. Instead, it served as a statement, a quiet declaration that we are here, that we are capable of understanding the universe, and that we are curious about who else might share it with us. In the end, the search for life is not only about finding answers, it is also about recognizing that we, too, are part of the same vast and silent landscape, visible to others in ways we are only beginning to understand. That message, encoded in a simple pattern, also included a representation of the very instrument that sent it, a quiet signature of its origin. It was a way of saying not only who we are, but how we reached out. But there is another, slower way to communicate across the stars. Instead of sending signals, we can send objects. Humanity has already done this through Voyager 1 and Voyager 2, both launched in the year 1977. These spacecraft continue their journey outward even now, drifting beyond the boundaries of our solar system. In the year 2012, Voyager 1 became the first human-made object to enter interstellar space, carrying with it a small but meaningful message. Attached to each probe is a golden record, a carefully prepared collection of sounds and images intended to represent life on Earth. It contains greetings in 55 human languages, music from different cultures, and recordings of natural sounds such as waves, wind, and animal voices. There are also images, over 100 in total, showing human life, landscapes, and basic scientific information, including the structure of DNA and our position within the solar system. Even the record itself includes instructions, along with a stylus, allowing it to be played by anyone who might find it. A map of pulsars is etched onto its surface, offering a way to locate our position in the galaxy. It is, in a sense, a message placed into the current of space, with no guarantee of arrival. The limitation of this approach is not technology, but time. Voyager 1 will pass near the star Gliese 445 in about 40,000 years. Voyager 2 will approach Ross 248 in roughly 42,000 years. And only after hundreds of thousands of years will either come close to brighter stars like Sirius. These timescales stretch far beyond any human expectation. And yet, even without direct messages, it is possible that distant observers could detect our presence, just as we study the subtle motion of stars to find planets. Another civilization could observe our sun and notice its slight movement caused by the gravitational pull of Earth and the other planets. From this, they could estimate the masses and orbits within our system, slowly building a picture of our world. Now imagine, for a moment, that contact were somehow established with a civilization near Proxima Centauri. Even in that best-case scenario, communication would be slow. A single message would take more than 4 years to arrive, and another 4 years for a reply to return. Conversations would unfold over decades, shaped by patience rather than immediacy. And if, beyond communication, we imagined a meeting, the challenge would grow even greater. With current propulsion, a journey to that nearby star would still require tens of thousands of years. Even at the speed of light, which remains beyond our reach, the trip would take several years. These limitations do not end the search. Instead, they define it. They remind us that exploration, at this scale, is not measured in moments, but in generations. And perhaps that is part of what makes it meaningful. If we extend this idea even further, beyond our nearest stars, the scale becomes almost impossible to hold in mind. The Milky Way itself stretches across roughly 100,000 light-years. To cross it from one side to the other would take 100,000 years at the speed of light. And since we are far from achieving such speeds, any realistic journey would take far longer. So we are left with difficult choices. Either we find a way to move faster than our current understanding of physics allows, or we accept a different kind of voyage, one that spans generations. A spacecraft carrying not just explorers, but entire communities, traveling from star to star over thousands of years. In such a journey, those who arrive would be distant descendants of those who first departed, separated not only by space, but by time itself. And while these ideas remain far in the future, our ability to observe distant worlds continues to improve here and now. The James Webb Space Telescope, designed to extend beyond the capabilities of the Hubble Space Telescope, has already begun to reveal details that were once beyond our reach. Among its many observations, it has detected faint infrared emissions from distant planetary systems, signals so subtle that they would have been invisible to previous instruments. At one point, attention focused on a faint glow originating from trillions of miles away, raising a quiet but compelling question. Could such a signal ever represent something artificial, or is it simply another natural process waiting to be understood? To explore that question, it helps to look at a specific system that has already reshaped our expectations. The star Trappist 1 hosts a group of 7 rocky planets, all relatively close in size to Earth. When they were first discovered, this system became one of the most promising locations in the search for habitable worlds, largely because several of its planets orbit within the region where liquid water could exist. More recently, observations from the James Webb Space Telescope focused on one of these planets, Trappist 1b. using its infrared instruments. Scientists measured the planet's thermal emission, effectively detecting the heat radiating from its surface. The results were both impressive and sobering. For the first time, such a faint signal had been measured from a rocky planet of this scale. But what it revealed was not a temperate world. Instead, Trappist 1b appears to be extremely hot, with temperatures around 450 degrees Fahrenheit, far beyond the range where liquid water could exist. It also shows little evidence of a substantial atmosphere, suggesting a surface exposed directly to intense stellar radiation. This outcome highlights an important pattern. Even when a planet lies within what we call the habitable zone, its actual conditions can be very different. Factors such as atmospheric composition, stellar activity, and orbital dynamics all play a role, and sometimes they combine in ways that make a planet far less hospitable than its location might suggest. At the same time, the observation itself marks a significant step forward. Detecting such faint infrared signals from small, rocky planets was once beyond our capabilities. Now, it is becoming part of a growing toolkit, allowing us to study these distant worlds in increasing detail. The TRAPPIST-1 system remains important, not because every planet within it is habitable, but because it shows how diverse planetary environments can be, even within a single system. It also reflects a broader trend. Stars like TRAPPIST-1, small, cool, and relatively common, may host a large number of rocky planets. In fact, within our galaxy, such stars are more numerous than stars like our Sun, and they may be even more likely to host planets. This raises a quiet but meaningful possibility. The kinds of worlds we are searching for may not be rare exceptions. They may be woven throughout the galaxy, waiting to be studied, one by one. And as our instruments continue to improve, we move a little closer to understanding not just where these planets are, but what they are truly like, and whether, somewhere among them, the conditions for life have taken hold. Stars like M dwarfs have become some of the most important targets in the search for habitable planets. They are smaller, cooler, and far more common than stars like our Sun, which makes them easier to study. When a rocky planet orbits close to such a star, its effects on the star's light are more noticeable, allowing us to detect and analyze it with greater precision. But there is a trade-off. These stars are often far more active than they first appear. They can produce frequent flares, releasing bursts of high-energy radiation that may gradually erode planetary atmospheres or disrupt any stable conditions on the surface. What seems like a promising environment from a distance can become far less hospitable upon closer inspection. This is exactly what we are beginning to understand with TRAPPIST-1. B. Earlier observations were not sensitive enough to determine whether this planet had an atmosphere or whether it was simply a bare, rocky world. Now, with more precise data, a clearer picture has emerged. The planet is likely tidally locked, meaning one side is always exposed to its star while the other remains in permanent darkness. In theory, if an atmosphere were present, it could help redistribute heat, creating more balanced conditions across the surface. However, measurements from the James Webb Space Telescope suggest something different. The recorded temperatures are higher than expected for a planet with a stable atmosphere, indicating that heat is not being evenly distributed. This strongly suggests that TRAPPIST-1b lacks a significant atmosphere altogether. As a result, it is no longer considered a strong candidate for habitability. And yet, this is not a failure. In many ways, it is progress. The real significance lies in the fact that we are now capable of making these measurements at all. For the first time, we can begin to directly assess the atmospheric conditions of small, rocky exoplanets. Each observation, even a disappointing one, sharpens our understanding. Looking ahead, scientists already have a general idea of what they are searching for. A truly favorable world might be somewhat larger than Earth, with a thicker atmosphere capable of retaining heat and protecting the surface. A global average temperature somewhere around 77 degrees Fahrenheit would allow liquid water to exist comfortably, supporting stable climates and potentially diverse ecosystems. But finding such a planet is not simple. It has often been compared to spotting a faint flicker of light in a vast, dark forest. To overcome this, astronomers rely heavily on the transit method, carefully observing stars over time and looking for small, repeating dips in brightness. By analyzing these subtle changes, they can determine whether a planet is present, estimate its size, and calculate how close it orbits its star. From this, they begin to infer whether conditions might fall within the habitable zone. One such discovery is Kepler 22b, located in the constellation Cygnus. At first glance, it may not seem extraordinary, but it orbits within the region where temperatures could allow liquid water to exist, making it an intriguing candidate for further study. The concept of the habitable zone, sometimes called the Goldilocks zone, describes this balance. A planet must be positioned at just the right distance from its star. Not so close that water evaporates, and not so far that it freezes. Within this narrow range, conditions may allow oceans to form and persist. And oceans, if they exist, can do more than support life. They can stabilize a planet's climate. Large bodies of water absorb heat and redistribute it, softening temperature extremes between day and night, between equator and poles. In this way, a planet covered in oceans may become more stable, more resilient, and perhaps more capable of sustaining life over long periods of time. As we continue to observe these distant worlds, we are not just searching for planets. We are learning how environments form, how they evolve, and how delicate the balance must be for life to emerge. Oceans, if they exist, do more than simply hold water. They act as a kind of quiet regulator, absorbing heat where it is abundant and redistributing it across the planet. In regions exposed to constant starlight, they can soften extreme temperatures, while in colder areas, they release stored warmth, preventing deep freezes. In this way, a planet covered in water may maintain a more balanced and stable climate over long periods of time. On Earth, such balance did not appear instantly. In its early history, our planet was far more hostile, shaped by intense heat and constant impacts. Over time, interactions with Moon helped stabilize its rotation and tides, allowing water to spread and settle. Gradually, conditions shifted, transforming a once volatile world into the environment we now recognize. This perspective makes planets like Kepler 22b especially interesting. Its orbital period is similar to Earth's, suggesting a familiar rhythm of seasons. Estimates indicate that if it lacks a strong atmosphere, its average temperature might remain quite low, around 12 degrees Fahrenheit. But if it possesses an atmosphere similar to ours, that temperature could rise significantly, perhaps reaching something closer to 72 degrees Fahrenheit, a range where liquid water could persist comfortably. The planet orbits a star, not unlike our Sun, though slightly dimmer and cooler. Because of this, it must orbit somewhat closer to receive a similar amount of energy. In fact, if placed within our own solar system, its position would fall somewhere between Earth and Venus. This alignment suggests that, at least in terms of incoming energy, conditions might not be too different from those we experience here. But there are important uncertainties. One possibility is that the planet's axis is tilted in a way that leads to extreme seasonal variation, perhaps even more pronounced than what we observe on Uranus. If that were the case, the climate could shift dramatically over time, with long periods of intense heat followed by extended cold. Another factor is gravity. Kepler 22b appears to be significantly larger than Earth, which implies a stronger gravitational pull. On such a world, movement would require more effort. And over time, any life that developed there might adapt in different ways. Structures might be lower and more compact, and biological systems could evolve to handle increased physical strain. Yet even with these considerations, one fundamental question remains unresolved. What kind of planet is it, truly? Despite its promising position, we do not yet know whether Kepler 22b is a rocky world like Earth, a planet covered entirely in deep oceans, or something closer to a small gas-rich world. If it were a water world, its oceans might extend for thousands of miles in depth, with no visible land at all. In such an environment, life, if it exists, would be entirely ocean-based, evolving under conditions very different from those on Earth. It is even possible that entirely unfamiliar ecosystems could emerge, shaped by pressure, chemistry, and energy sources we are only beginning to consider. These possibilities remain open. And for now, Kepler 22b exists not as a defined destination, but as a question, one that invites further observation, and perhaps, one day, a clearer answer. There is also another possibility that cannot yet be ruled out. Kepler 22b may not be a rocky world at all. Some models suggest it could belong to a category often described as a mini version of Neptune, a planet with a thick, gaseous envelope surrounding a dense core. If that is the case, then its surface, at least in the way we imagine it, may not exist at all. But even if we assume, for a moment, that it is a solid Earth-like planet, much remains unknown. We do not yet know whether it has an atmosphere, and if it does, what that atmosphere is made of. It could be relatively mild and stable, or it could be dense and hostile, more similar to Venus, where extreme conditions make the surface uninhabitable. And yet, for the sake of understanding, it is sometimes useful to imagine what such a world might be like under more favorable conditions. If Kepler 22b were rocky, with a stable atmosphere and liquid water, its stronger gravity would shape both its landscape and any life that might exist there. Mountains could rise sharply, valleys might run deep, and rivers could carve their way across the surface with steady force. Over time, these features would create a world both familiar and subtly different from our own. Life, if present, would likely adapt to these conditions. Plants might grow shorter and sturdier, anchored firmly against the pull of gravity. Animals, too, could evolve in ways that reflect the environment, perhaps becoming smaller in size but stronger in structure, with limbs built to support greater weight. Movement itself would require more energy, shaping behavior, biology, and even ecosystems in ways we can only begin to imagine. And yet, all of this remains speculation. At present, we do not have enough data to confirm the true nature of this planet. It may be rocky, or it may not. It may have oceans, or it may be entirely different from anything we have seen before. This uncertainty points to a broader truth about the search for life. Water, while essential, is only one part of a much larger equation. For life to emerge and persist, many conditions must align. A planet must orbit within the habitable zone, where temperatures allow liquid water to exist, but it must also have sufficient atmospheric pressure, a stable climate, and protection from harmful radiation. If a planet orbits too close to its star, water will evaporate, leaving a dry and hostile surface, as we see on Venus. Too far, and water freezes, potentially locking it beneath layers of ice, as may be the case in the outer regions of our solar system. A balance must be maintained, not just in distance, but in many interconnected factors. Across the Milky Way, there are countless stars, and around many of them, planets. Among thousands of known exoplanets, scientists have identified a smaller group that may be especially favorable for life, sometimes referred to as superhabitable worlds. These planets are often slightly larger than Earth, with stronger gravity and thicker atmospheres, conditions that may support greater biodiversity over long periods of time. Even the type of star matters. Smaller stars, with longer lifespans, may provide stable environments for billions of years, giving life more time to develop and evolve. In contrast, larger stars may burn too quickly, ending their lifetimes before complex life has a chance to emerge. And so, the search continues, guided by a growing understanding of what makes a world not just habitable, but truly alive. Each discovery adds a small piece to this larger picture, bringing us closer to answering a question that has followed us for generations. Are we alone, or are we simply one example among many, scattered across the quiet expanse of the universe? The lifetime of a star plays a quiet but essential role in the story of life. Our own sun, for example, is expected to exist for less than 10 billion years, and on Earth, it took roughly 4 billion years for complex life to emerge. This raises an important consideration. Some stars may simply not last long enough for life to fully develop on the planets that orbit them. Because of this, scientists have begun to look more closely at smaller, longer-lived stars, red dwarf stars. Though dimmer and less energetic than the Sun, can remain stable for tens of billions of years. In some cases, their lifetimes may extend from 20 to 70 billion years, offering a far longer window for life to form, evolve, and adapt. On planets considered potentially more favorable than Earth, sometimes referred to as superhabitable worlds, conditions might be slightly different from what we experience here. Average temperatures could be a little higher, perhaps by around 8 degrees Fahrenheit, and the presence of water might be more abundant, not only in oceans, but also in clouds and atmospheric moisture. Such environments could support a richer diversity of life, with climates that remain warm and stable over long periods. So far, a small number of these candidates have been identified, many of them located more than 100 light-years away. With the continued development of advanced observatories, we may soon begin to understand whether these worlds truly possess the conditions we are looking for. One nearby example is Teegarden B, orbiting Teegarden's star at a distance of about 12 light-years. Unlike many red dwarfs, this star appears relatively calm, which may allow its planet to retain an atmosphere. Teegarden B has a mass similar to Earth, but its orbit is much tighter, completing a full revolution in just a few days. This creates a very different sense of time, where a year passes almost as quickly as a week. Further away, in the constellation Cygnus, lies Kepler 1, 638b, a much larger world classified as a super-Earth. It is roughly twice the size of our planet and significantly more massive, which implies a stronger gravitational pull. On such a world, even simple movement would feel more demanding. And any life that exists there would likely be adapted to these conditions. Another example is LHS 1140b, a dense and rocky planet with a mass several times that of Earth. Its gravity is strong enough that standing or moving would require considerable effort by human standards. At the same time, its thick atmosphere may help retain heat, potentially allowing surface temperatures to remain above freezing in some regions. Each of these worlds offers a slightly different version of what a habitable planet might be. None of them perfectly match Earth. And perhaps that is the point. The universe does not seem to repeat the same conditions exactly. Instead, it produces variations, each shaped by its own balance of factors. And as we continue to observe these distant planets, we are slowly learning that habitability is not a single fixed idea. It is a spectrum, a range of possibilities, each one expanding our understanding of where life might exist and what forms it might take. Within the Trappist, one system, there are worlds that continue to draw attention. including smaller planets that orbit within the habitable zone. One of them is significantly lighter than Earth, with gravity that would feel noticeably weaker, perhaps closer to half of what we experience here. Under such conditions, movement would feel easier, almost effortless compared to Earth, though still far more stable than what astronauts experienced on the Moon, where gravity is only a small fraction of our own. Further out, another intriguing world appears around Kepler 452b, orbiting a star that closely resembles our Sun, though slightly older. This system offers a glimpse into what a more mature version of our own solar system might look like. The planet itself has existed for billions of years longer than Earth, suggesting that if life had emerged there, it would have had far more time to evolve. But distance once again becomes the limiting factor. Even with our fastest spacecraft, such as New Horizons, a journey to such a world would take tens of millions of years. These planets may be conceptually close, but in practice, they remain far beyond our reach. Which brings us back to Proxima Centauri b, still the nearest known Earth-sized world. It orbits Proxima Centauri at a distance of just over 4 light-years. In astronomical terms, this is our closest opportunity. Its size and mass are similar to Earth, though its true nature remains uncertain, and it may differ significantly beneath the surface. Despite this proximity, even reaching Proxima Centauri b presents a profound challenge. With current propulsion methods, travel would take well over 100,000 years. Our fastest rockets, moving at several times the speed of sound, are simply not designed for interstellar journeys. This is why more speculative ideas continue to be explored. Among them is the concept of a warp drive, a theoretical approach based on manipulating space itself rather than moving through it in the conventional sense. Instead of accelerating a spacecraft to extreme speeds, the idea is to compress space in front of it and expand space behind it, effectively allowing the craft to move faster than light relative to distant observers, while remaining locally stationary within its own frame. This concept, often associated with the Alcubierre drive, remains purely theoretical. It would require enormous amounts of energy, potentially comparable to the output of an entire planet like Jupiter, and relies on forms of matter and energy that have not yet been fully understood or even confirmed to exist in usable ways. Some refinements have suggested that the structure needed to generate such a warp field may not need to be perfectly symmetrical, but could instead take on more practical shapes, simplifying the design. Even so, these ideas remain far from implementation. And yet, they persist as possibilities. Not because they are easy, but because the challenge itself demands new ways of thinking. For now, we remain observers, looking outward with increasingly powerful instruments, mapping the stars, and studying the faint signals of distant worlds. The journey to reach them may still lie in the future, but the understanding we gain today is already reshaping how we see our place in the universe. If you find this kind of quiet exploration meaningful, consider following the channel to continue these journeys together, one question at a time, into the vast and still unfolding cosmos. Somewhere in the near future, missions are already being imagined that will attempt something humanity has never done before: to leave the solar system not just with instruments, but with intention, to explore worlds that may resemble our own. Organizations like NASA have outlined early concepts for interstellar travel, small beginnings for what could one day become something far greater. There are ideas, still uncertain, that light itself could be used as a form of propulsion, if a probe is made small enough, almost weightless. It might be pushed forward by powerful laser beams, gradually accelerating to a significant fraction of the speed of light. Other possibilities remain more distant, drawing from nuclear energy, or even the theoretical reactions between matter and antimatter, concepts that exist more in equations than in reality, at least for now. All of these approaches share something in common. They are not yet solutions. They are questions. quiet explorations of what might one day be possible. And so, for the moment, we remain here, looking up at the night sky, knowing that beyond those distant points of light are worlds we have only just begun to understand. Some may be barren, some may be hostile, and some, perhaps, may be quietly waiting. We do not know how long it will take to reach them. We do not know what we will find when we do. But the search itself continues, slowly, patiently, carried forward by curiosity. And maybe that is enough for now. So as the universe drifts on in silence, and the stars continue their distant motion, you can simply rest with that thought. That somewhere, far beyond what we can see, there are still stories unfolding. And we are only at the very beginning of listening